All right, hi everybody. So the question here says the population of a city is increasing by 3% every 10 months. Okay, now that's a little off there. That period isn't a complete year. Okay, that 3% is per every 10 months, so that 3% isn't even per annum. So it's a little bit of a different way of approaching a problem like this. It says the current population is 46,000. What will the population be in 5 years? Okay, well, we're looking at exponential growth. So this is going to be AB to the X. There's our model. Now, I like using the compound interest equation to model population growth because money, people behave the same way. Okay, they both kind of grow in an exponential way here. So that's a good model here. I also kind of like the compound interest equation. Sorry, not the compound interest equation. This is the growth formula, the periodic growth formula. So this is the half-life equation, if you will. We use this for half-life questions or if something's doubling or tripling. Now, I'm going to focus on this version right now. I want to figure out what the population is going to be. I'm going to start with 46,000. Now, what I like about this equation is that it forces me to look at this 1 plus I. Because my population is increasing by 3%, I start at 1 and I add 0.03. There's an increase from 100% by 3%. Awesome. Now, normally I would have up here the number of compounding periods. I mean, if I'm using this as the compound interest equation. But it's a little bit more complicated here because my compounding periods, okay, where that 3% gets added, doesn't quite line up with the number of years. It's a little bit off that. So I'm going to take my clue from this other equation. I'm going to kind of mix these together. So it's going to be there for 5 years, but I'm actually going to convert that into, I'm going to divide that by the period of the growth here. And that's going to give me the number of times that I have this 3% multiple take over here. So the period of this growth is going to be, well, the 5 is in terms of years, so, and my 3% is in terms of every 10 months. I'm going to convert that 10 months into a year, into a fraction of a year. That's going to be 10 divided by 12. So I'm going to take that 5 years, I'm going to divide that by the period in years, which is going to be 10/12. Now it turns out when you evaluate that exponent, you get 6. And that actually makes perfect sense. In 5 years, you'll have 6 groups of 10 months. And every one of those 10-month groups is going to increase the population by 3%. Okay, so let's go to our calculator. Let's evaluate that. So 46,000 multiplied by 1 plus 0.03, there's my 3%, to the power of, and I know that's going to be 6, but maybe what I do is I multiply by, so I have 5 divided by, in brackets, 10 divided by 12. Just so that you believe me that I'm not doing anything magical there. Press the button and I get, here we go, 54,926, okay, 0.40564, dot, dot, dot. All right, now, we're going to have a little discussion about this. What do you do with this number? How many people does that represent? Okay, now I had a teacher come in and work with me and explain to me that when you get it to this point right here, 54,926, with that decimal there are good statistical reasons why you might round that up or you might round that down. Okay, so you could go one way or the other. And so this is one of those times here where I would look to my class, I'd say, okay, what do we make of this little bit right here? And there's always somebody that says, oh, what is that 0.4? Maybe that's a baby that hasn't been born yet. That's the 0.4. Or maybe that's somebody who hasn't got any arms and whatnot. And so then I automatically counter with that. Okay, hey, if you walk up to someone with no arms and you say, hey, you're only like a fraction of a person, that person's going to kick the stuffing out of you. And I do that to make a laugh, right? Because I'm hoping that they'll kind of clue in and remember, because they laughed a little bit, they'll remember the concept here. But it's actually not all that funny to think of it like that. There are lots of people all over the place that are treated as if they're just fractions of people. Okay? My equation here doesn't care whether you're, what race you are, what orientation, what religion, what you look like. Okay? It doesn't care. It adds everything up here, but it doesn't quite know what to do with that fraction that's left over. You know, let's just make that a rule that when it comes to people, we're going to round up. Okay? So instead of being 54,926, even though that's 0.4, let's make that 7. Okay? Let's round that up. In fact, I would challenge you that even if this question said, for example, even if at the end here it said to the nearest whole, okay, I challenge you to just round that up instead and say, you know what, write down there, even just write it on your sheet there. When it comes to people, okay, when it comes to people, I round up. Okay. Now, I don't know, maybe you lose a mark for that. But you know what? Yeah, that seems like an important thing to think about here. In fact, you might say, well, you might even say, you know, is it worth losing a mark here just to make this kind of a little political statement? I don't know, maybe you got that backwards, you know. Is it worth a mark to round down? Okay, to imply that somebody is worth rounding down. You know, I think if you wrote that, kind of take that risk there, maybe you and your teacher are the only ones that are going to see it, but I don't know, maybe that inspires your teacher to teach next time and say, you know, when it comes to people, we round up. Maybe that becomes the new rule. Maybe that should be the rule. Okay, when we're talking about people, doesn't matter, we always round up. Okay, I know that got a little preachy at the end there. Sorry about that, but I'm going to leave it in.